Welcome again to the video lecture series for GG and OCN 312. This video is about partial derivatives. The reading is section 13.3 of Greenberg's text, and I encourage you to look at that carefully. What I'll cover in this relatively short video is, first of all, the concept of functions of multiple variables. I'll then define what a partial derivative is, and then we'll show how to take partial derivatives of some example functions. What I'd like you to learn by the time you've viewed this video, as well as did the practice problems in the problem sets, is that you will know what a partial derivative is, and you'll also know how to compute and manipulate them just as well as you can an ordinary derivative. Now, so far, we've discussed functions of a single variable. For example, when we talk about f, a function of x, this means that f varies only with x. And x is we've referred to x as the independent variable. Okay, and if f only varies with respect to x, then the only derivative we can take is with respect to x. So we can describe f prime being the derivative of f with respect to x, evaluated at some location, in this case x. And so this describes the rate change of f as you change x. It's the rate change of f with x at point x. But often, functions will encounter problems involving functions of multiple variables. Or multiple independent variables. And the image below is an example of topography. So in this case, f of x and y. F is now a function of x, which, for example, could be latitude, and y, which could be longitude, and f is the topography. In this case, around the Hawaiian Ridge. And I've displayed this data a number of different ways. This bottom plot here is a contour plot. I'm not sure if you can see my cursor here. This is a contour plot of topography. This is the big island of Hawaii. This direction is north, and you can see Hawaii marching up through Maui, Molokai, Oahu, and Kauai. And the topography is contoured here, and it's also projected here as a three-dimensional perspective plot. So you can see that it's extremely vertically exaggerated, so the slopes are much higher, but you can see that the Hawaiian Ridge has substantial topography, and it varies as a function of x, which could be latitude, longitude, or y, which could be latitude. It's also displayed right here as a colored contour plot or colored perspective view. So that's one example. And given a function of multiple variables, we can also take derivatives of the function with respect to each of the independent variables. So for example, say we have a function that f that varies with x and y. We can take the derivative of f with respect to x, and when we do that with respect to one variable, this is called a partial derivative. And we use the curly d's to represent partial derivatives. I guess curly d indicates partial derivatives. So the partial of f with respect to x is defined as the limit as delta x goes to 0 of f evaluated at point x plus delta x and at point y minus f evaluated at point x and y all over delta x. So what I've written is the partial derivative of f with respect to x evaluated at point x and y. We can also abbreviate this as follows. We can abbreviate partial f with respect to x evaluated at point x and y as f sub x evaluated at point x and y. So these are equivalent symbols. This is just a slightly shorter way of writing it. Likewise, we can take the partial of f evaluated at x and y with respect to y. The partial derivative with respect to y evaluated at point x and y. And we can also write that as f sub y. And that's equal to the limit as delta y goes to 0 of f evaluated at point x and y plus delta y minus f evaluated at point x and y divided by delta y. And again, that's the limit as delta y goes to 0. So let's look at another graphical example. So this is a three-dimensional sort of surface plot of a function that varies in x and in y. And this function is cosine x divided by 4 times sine y divided by 2. So I'll just turn it around so you can get a better sense for how it's behaving. So it's varying in y as a full sine function, and the wavelength of the cosine function is twice that of the sine function. Okay, and so we can you can imagine looking at how the function varies in one dimension. Okay, so this is This is how the function varies with x at a y value of 1.6. That's what this line shows. And we can interpret the partial derivative of this function with respect to x as the slope of this curve in the x direction, right? So in this case, y is a fixed value, and we can evaluate the partial derivative everywhere along the curve, and with respect to x, it's the slope in the x direction. Likewise, we can evaluate the slope at the same point as a function or in the y direction. The partial derivative of f with respect to y at this point is can be interpreted as the slope of this surface in the y direction. So that's an interpretation of these two partial derivatives. Now let's talk about notation. We'll talk about notation as well as how to take more or higher partial derivatives. So higher partial derivatives. So we can take, if we have our partial derivative of f with respect to x, for example, we can take the derivative of that with respect to y, and we can write that as the second partial with respect to y and x. And that's, we can also note that or write that as fxy. So we're this is the variable we write first is the first derivative we take. And then the second variable is the second derivative taken. That's, in other words, we take the derivative with respect to x, and then we take the derivative with respect to y. Similarly, we can take the derivative with respect to y first, and then take the derivative with respect to x, and we can write that again as the second partial with respect to x and y, and that's noted as f. In this case, the first derivative is with respect to y, and the second is with respect to x. Okay, and we can also take the derivative of f with respect to x twice, and that's second partial with respect to x twice, and also written as f sub x x. And we can take the derivative of f with respect to y twice, second partial of f with respect to y is written also as f sub y y. One aspect to note is that if, going back to our mixed partial derivatives, one aspect to note is if the partial of f with respect to x evaluated at a given point, as well as the partial of f with respect to y at that same point, are both continuous. They're continuous functions. That is, they have no breaks. No gaps or breaks. no gap or break near point x0, y0, then the partial of f with respect to y followed by x, if we take the partial derivative with respect to x first and the partial derivative with respect to y second, that's equal to the partial of derivative of f with respect to y followed by the partial derivative with respect to x. So this is the case if these functions, if the first derivatives are continuous at that point. So let's look at one example of a function, and here I'm going to show how to evaluate these partial derivatives. So say f of x and y is equal to 3x squared plus 4xy minus 2y squared. Then we can evaluate the partial with respect to x. What we do is just treat y as a constant when we take this partial derivative, and we just take the derivative with respect to x. So the first term gives us 6x. The second gives us 4y, because again we're treating y as a constant. And the last term is equal to 0. The partial with respect to y is taken by treating x as a constant. We're evaluating this at a constant value of x, and we're taking the derivative with respect to y. So the first term is 0 in this case. The second term is 4x, and then the last term is 4y. So in the first case, we held x constant, and in the second case, we held y constant. And so if we were to take the derivative with respect to y of f of x, then we can take the derivative of this function, and again we're going to hold, since we're taking the partial with respect to y, we would treat x as a constant, and so the only part that varies with y is the second term, and this gives us 4. The derivative with respect to x of partial f y is taking the derivative with respect to x of this equation, and again we're going to hold y constant, and so the only term that varies with x is this 4x, and that's equal to 4. So in this case, these two functions were continuous about x and y, so we found that the mixed partial derivatives, the order of differentiation here didn't matter. They both equaled each other. And then finally, the second partial with respect to x is evaluated by taking the derivative of this function with respect to x, holding y constant, and that gives us 6. And then the derivative, second partial with respect to y, is evaluated by taking the derivative of this function, holding x constant, and that gives us minus 4. Okay, so those are some examples of how to evaluate partial derivatives of functions of multiple variables. In engineering and earth science, partial differential equations, or equations involving partial derivatives, are widely used. They're very powerful ways of describing physical systems. And we'll talk about this a bit more in class, and you'll get a chance to work out some problems on manipulating these partial derivatives with your problem sets.